Alrighty, good morning, lads and ladies. Sorry, I'm a few minutes late there. I was just buttoning up your take-home test. So today, we're going to cover the last little bit of material for the class. And I know it might seem a little bit odd that, the one lecture here between that last test and the next one. This is why the next one is going to be a take-home, but the material is actually very easy. So I think you guys will not have a difficult time with it. If you do want to talk about anything following today's class, you can of course come to office hours or reach out to me. I can set up an extra meeting through Zoom for anybody who would like. But without further ado, let's get into it. I'm using graph paper today because what we're going to be talking about is actually really useful here. Let's take a look. So the new topic is systems of equations and systems of inequalities also. This is MAC1105, section 007. It is our last lecture. Today is the 22nd, right? Yeah. And today, we're going to talk about systems of equations and inequalities. So normally I would do this over a full week. Normally we would have 2 classes on these topics. And if we're not able to get through everything here today in a clean and appropriate pace, then I'll record an extra lecture this evening for you guys to watch. But it all depends on how things go. As with all things mathematics, if we're starting with a totally new topic, there's only one place to begin, and that's kind of with a definition. Unfortunately, definitions here don't tell us a whole lot as far as like how to solve the things, but we'll show it. A system of equations or inequalities is a collection of those things, of equations or inequalities meant to be solved simultaneously. So when I was in school, they actually called these simultaneous systems, just to be redundant and make sure that was clear. But these days, we just usually call them systems. So what does that even mean? Well, it means we give you multiple equations, usually with multiple variables. And your objective is to find the numbers you could plug in for those variables that make all the equations true at once. This is something that you've seen in 1033, almost certainly seen in high school. So rather than spending a bunch of time going over what the things are, I just want to kind of show you how to solve them and give you a little bit of a feel for the different kind of solution spaces you can get. Before I show you an example, though, there's 1 or 2 things I want to talk about regarding classification. We're going to begin with systems of equations. But they can be classified into 2 major groups. Groups. The first is linear systems. And this goes for systems of equations and systems of inequalities. Both can be classified into these two groups, the first of which is linear, and the second is nonlinear. So we've talked in this course about what makes an equation or a function linear or nonlinear. Remember, a linear equation is an equation where all the variables that show up are raised just to the first power, never squared, never under a square root, never downstairs in a fraction, never anything like that. So a linear system, this is a system where all the equations or inequalities are linear, right? Meaning the variables only show up raised to the first power upstairs, never under a radical, never downstairs in a fraction, never with a power of 2 or 3 or anything like that. A nonlinear system, this is a system where at least one equation or inequality is not linear. It turns out that we like linear systems way, way more. The study of linear systems leads to this whole subset of advanced algebra called linear algebra. Linear algebra, turns out, is like the heart of quantum physics. It's the heart of statics, if you're interested in engineering. It's the heart of so many different areas in mathematics and engineering and science that we really, really do love linear systems. Nonlinear systems, these tend to be a pain in the ass. Basically, mathematicians know all there is to know about linear systems. We have categorized them. We have built entire schemes of mathematics around them. And if you give me a linear system, you just write down a random linear system, I can tell you how many solutions it has. I can tell you how long it's going to take to find those solutions. And I can find those solutions if they exist. 100% guaranteed. Nonlinear systems, on the other hand, it's very easy to, if you just write down a random nonlinear system, write one down that first could have no solutions, second could have solutions, but that we just can't find. So it turns out nonlinear systems are quite nasty, whereas linear systems are quite nice. So these are very nice. These are quite nasty. So let's see if we can classify some systems as to whether or not they are linear or nonlinear. Actually, let's do x squared minus y. Yeah, sorry. Squared minus y equals 0 and x plus y equals 1. And, okay, so I have here 4 systems. the top two are systems of equations, A and B. These are systems of equations because you see each one of the things is an equation. So within A, I have the equation 2x plus 3y equals 1 and x minus 2y equals 0. So this is a system of equations, and I want to know, is this linear or non-linear? So you can tell me in the chat if you think this system is linear or non-linear based on the definitions we have up here.
Linear.
Yeah, very good. This is a linear system because each of those equations is a linear equation, right? 2x plus 3y equals 1. If you think about that equation, that's the equation of a line. It's in standard form here. You could put it into y equals mx plus b if you wanted. Or you could just note that, yeah, x is showing up here and it's raised to the power of 1. It's not under a radical. It's not downstairs in a fraction. And the same is true of y. Y is showing up upstairs to the power of 1, not under a radical or anything like that. So this is definitely a linear equation. And exactly the same logic shows that this is a linear equation. So since all of the equations in this system are linear, the whole system is called a linear system. So this one is linear. Okay, what about B?
Non-linear.
Good. Yeah, that's correct. This is nonlinear. Can you tell me why this is nonlinear?
Because x is squared.
Yeah, perfect, right? It's that easy. The system B is nonlinear because in the first equation, we have an x squared here. So if you have any of the variables raised to any power other than 1, then that equation is nonlinear. And if any of the equations are nonlinear, the whole system is nonlinear. What's the graph of this equation look like? X squared minus y equals 0. Is there another way to write that? Yeah, if I add y to both sides, this is the same as x squared equals y, or y equals x squared. We know that graph, that's a parabola. Not a line. So this is not a linear equation. Even though the second equation is linear, it doesn't matter. Remember, if any of them, any of the equations are nonlinear, the system is nonlinear. All right. See here, this is a system of inequalities, right? Rather than two equations, what we have are two inequalities. Rather than an equal sign here, we have a greater than sign and a less than sign. I'm going to show you how to graph these and stuff like that. But before we do that, I just want to learn how to classify them. So is the system of inequalities in C linear or nonlinear? Good. This would be a linear system. Because both of these inequalities are linear inequalities. You learned in previous algebra classes, 1033 or high school, how to graph these. I'm going to remind you how to graph an individual linear inequality, but basically you just sketch the line and then you either shade above or below. Since if you swapped the greater than here for an equals, you would get the equation of a line. We call this a linear inequality. And the same is true of the one below. So it's exactly the same criterion as for systems of equations. You look and see whether each of the things is linear. And in this case, since the powers of x and y are both 1, they're both showing up upstairs, not underneath any radicals or anything like that. This is a linear system. Now, part D, this is a little bit weird. We've got an inequality in one and an equation in the other. Solving things like this can be very, very hard, can be very, very strange. But classifying it as linear or nonlinear is quite easy. Who can help me out? Is the object in D, the system here, linear or nonlinear? Yeah, perfect, Jacob. This is nonlinear. And that's because the inequality x squared plus y squared is less than or equal to 1 is nonlinear. You have variables showing up raised to the power of 2, right? Which is definitely not a linear thing. This inequality defines what's called the unit disk. X squared plus y squared is less than or equal to 1 is a circle of radius 1 centered at the origin with all the center filled in. Okay, so classifying systems as linear or nonlinear isn't tricky. I want to now talk a little bit about how to solve linear systems, specifically linear systems of equations. So we're not going to worry about inequalities at first. We're going to worry about equations at first. Any questions on this example? Okay, I'm going to refresh my copy and then we'll look at some examples of solving. All right. So solving systems of equations. Basically, there's two methods. First is one you're probably familiar with, substitution. To solve a system by substitution, you first solve one of the equations, solve one equation for one of the variables. You choose the variable you want to solve for. So you pick an equation, you pick a variable, and you solve that equation for that variable. Once you've done that, you then substitute the expression you found when you solved, substitute that expression back into the other equation. The result of this process, say you solve the first equation for y, and you get y equals some mess of things involving x. Then you take that and you substitute it in for y in the other equation. What that means is that your second equation now only has one variable. You solve the resulting equation for the single variable it now contains. So after that first step, you'll have like y equals x minus 7 or something like that. After the second step, you'll have like x equals 5. That gives you an actual solution for that variable. Finally, you plug that solution into either original equation to solve for the other variable. All right, so this is how you solve a system using substitution. Don't worry, I'm going to do examples. The other method, though, and this is the method that I want you to learn because I expect that you've seen substitution before. If you forget it, it's okay. We're going to go back through it. But I know most people are fairly comfortable with substitution at this stage. The other method is called elimination, and this is the method I really want you guys to learn. So this is where I give you a system, and you're going to add the two equations together, or maybe subtract the two equations from each other, or maybe add a multiple of one equation to the other such that one of the variables goes away. All of those are actually contained in the last. So you add a multiple of one equation to the other equation. Such that one of the variables goes away. So that will give you an equation with a single variable. If one of the variables goes away and you previously had two variables, then now you have one variable. Now we solve the resulting equation for its single variable. Finally, just like in the last one, our last step is to plug that solution back in to either original equation and solve for the other variable. Okay, so this is how we solve systems of equations algebraically. I'm going to talk about solving them graphically also, but solving a system graphically is something that we can only do sometimes, only if we're very, very lucky. But the graphical interpretation is still super important. I'll give you guys a second to write. I think having these in your notes will be useful so you can refer back to them if you do get lost. And then we're going to look at some examples. Okay. So it's one thing to write down some words, it's another thing to do it. So let's do it. Let's solve the system x minus y equals 0 and 2x plus y equals 3. And first, I'm going to do this by elimination. Well, maybe actually we'll do it first by substitution. That's probably what you're more familiar with. My goal here is to convince you that elimination is actually the better method. Okay. To solve this by substitution, remember first we solve one of the equations for one of the variables. So first I'm going to copy the system down. Of the two equations, I think the first equation here is the easier one to solve for one of the variables. So I'm going to begin by solving the first equation for x. That's my first step. So I've got x minus y equals 0. Solving linear equations is not hard. We've been doing it all semester. We just add the y to both sides here, and I get x equals y. My next step is to substitute x equals y in the second equation. So the second equation here is 2x plus y equals 3. And if everywhere there is an x, I write y instead. That's what we mean by substituting. I'll have 2y plus y equals 3. Right? So since x is equal to y by the first equation, 2x is the same as 2y. I'm swapping this guy right here for y. That's what we mean by substitute. If I'd gotten x equals 5y, then I would have put 5y here. If I had x equals y plus 1, I would have put y plus 1 here in parentheses. And now I solve this equation for its variable, right? Whatever the variable is here, the variable is y. So I have 2y plus y equals 3. That's the same as saying 3y equals 3, because 2y plus y is 3y. And then dividing both sides by 3, that's the same as saying y is equal to 1. So I get the first part of my solution here. I know that whatever the solution to the system is, the y value must be 1. And then finally, remember my last step is to take this, plug it back into either of the original equations to solve for x. Again, we have a choice here. So we're going to plug y equals 1 into either original and solve the result for x. Again, I think the first equation is easier to work with, so I'll use that one, but we would get the same thing either way. So if I take x minus y equals 0, and I plug y equals 1 in, then we get x minus 1 equals 0. And then I solve that for x minus 1 equals 0. That's the same as saying x equals 1. So the solution to this system is x equals 1 and y equals 1. Or we could write that as the ordered pair this is 1, 1. And there's a reason why we often like to think of these solutions as ordered pairs. I mean, there's an x value and a y value, sure. But there's also a geometric interpretation, which I'll show you in a second. The geometric interpretation is that the solution to a system of equations is the point where those two graphs touch. So this line and this line touch at the point 1, 1. Any questions about how we solved this system using substitution? Okay. I'm now going to solve the same system using elimination. How bad is this bleed through? It's not too bad. All right. X minus y equals 0, 2x plus y equals 3. So here's part B. Remember what the instructions for elimination said. You have to add a multiple of one equation to the other equation such that one of the variables goes away. What you want to do is look at the system and see what happens if I add the first equation to the second equation. Or what happens if I add 2 times the first equation to the second equation? Or what should I multiply the first equation by such that when I add that to the second equation, one of the variables goes away? Here, the multiple is very easy to choose. The first equation has a minus y, and the second equation has a plus y. So I don't need to multiply this by anything. If I just straight up add these equations to each other, you'll have negative y plus positive y, and the y's will go away. Adding the first and second equations gives, and I like to do it like this. I'll show you the notation. X minus y equals 0, 2x plus y equals 3. And I'll just draw a little thing here, just like you did in grade school, and put a little plus over here. And then you just add the columns. X plus 2x is 3x. Negative y plus positive y is 0y. And 0 plus 3 is 3. Everybody see what happened there? And the nice thing about this is that the y's go away. This just says 3x equals 3. So this is equivalent to just saying 3x equals 3. And now we solve the result for x. So 3x equals 3. We divide both sides by 3, we just get x equals 1. And right away, we get this guy. See how much faster this is? And your last step is to back substitute. Now we plug x equals 1 into either equation, either original, and solve for y. So maybe just for fun, I'll plug it in here this time. 2x plus y equals 3. If I plug in x equals 1, I get 2 times 1 plus y equals 3, which is the same as saying 2 plus y equals 3. And then subtracting 2 from both sides, we get y equals 1. So elimination much faster. And really the important step is this one. Because that's where we eliminated one of the variables. You see that the challenge is that both of these equations, and in general in systems, each equation has multiple variables. So you can't just solve for a number right away. You can solve for one variable in terms of the other, but in order to get a number for either of them, you need to somehow make one of the variables go away. You can do that either by substituting after solving for one of the variables in terms of the other, substituting that into the other equation, and that'll give you a single variable equation, or you can try to eliminate one of the variables like we did here. So again, here the solution is the ordered pair one comma one. So those are the very basics of substitution and elimination. Are there any questions at all on this solution, the elimination solution? I'd really love to hear what you're thinking, anything at all. Is anybody seeing elimination for the first time? Give me a thumbs up react or a nod in the chat, something. Let me know if this is your first time seeing the method of elimination. College algebra was the first time I saw this too. Okay. I mentioned earlier that linear systems are nice and that nonlinear systems are not so nice. When I say that linear systems are nice, again, what I mean is that we kind of know everything about them. You give me a linear system, I can tell you how many solutions it has. I can find those solutions if they exist. We can even do quite a bit more. I want to talk about why that's the case. And the geometry of linear systems. If you think about it, so I'll start with this note. The solution to a linear system or any system, really, not just linear system, the solution to a system of equations is the point or points where the graphs touch. So if you think about that last system, we had two equations. One of them, x minus y equals 0, is the same as y equals x. So that line looks like this. The other one, which is 2x plus y equals 3, is the same as y equals negative 2x plus 3. So he looks like this. So this is the line x minus y equals 0, and this is the line 2x plus y equals 3. And you see the point where these guys touch. The solution is the point 1, 1. So if you can graph the two lines, and you can see exactly where those two lines touch from the graph, then you don't even need to go through either elimination or substitution. You can just say, oh, the solution is that point where the two lines touch. Now, sometimes it's not easy to see that, like if the ordered pairs, if there are fractions in there or weird numbers in there that aren't integers, it can be tricky to tell the exact coordinates from the graph. But in this case, we can. And the geometric interpretation here, the fact that the solution to the linear system is the point where these two lines touch, is what's going to tell us why these systems are nice. Because two lines can only touch in so many ways. They're straight lines. They only have so many possibilities. So due to this interpretation, due to this geometry, linear systems have one of three possible solution, we'll call them cases. And they're broken down like this. If the lines have different slopes, if you graph two lines, but they have different slopes, then they will touch in one and only one point. All right, that's like the picture we have above. You see, no matter what those lines are, if one of them is like over here, and the other one is like over here, if the lines have different slopes, then you will have one and only one solution. Because two lines with different slopes always meet in a single point. So if the two lines have different slopes, then the system has a unique solution. Because two lines with different slopes always meet in one point. You might have to zoom out to find that point, but you might have to scoot around to find that point on the graph. But if two lines have different slopes, no matter what those slopes are, then those will meet in a single point. I can draw another picture here to try and illustrate this. Even if the slopes are kind of close to one another, like maybe something like this, and something like this. You know, maybe this is slope 1 and this is slope 1/2 or something like that. Still, they will meet in a single point, and that point is the solution. So that's the first case. Different slopes, unique solution, one solution. Two other cases. Might seem like maybe there's only one other case if they have the same slope, but believe it or not, that's broken down into two other cases. First of these maybe the lines have the same slope. Maybe, remember that means that the lines are parallel, but different y-intercepts. Meaning you have two distinct lines, but they are parallel. So maybe I have one equation whose graph looks like this, and another equation whose graph looks like this. Two parallel lines, they never meet. So because parallel lines never touch, these systems have no solution. What's missing from this picture? So we've got these two cases, right? But I said there are three possible cases. You could have different slopes. You could have the same slope but different y-intercepts. What else is possible? Well, you could have the same slope and the same y-intercept. In other words, the two lines could be the same line. They might be disguised algebra-wise. You might not be able to see it immediately from looking at the equations. But maybe I have one looking like this. And then when you graph the other one, he sits right on top of this guy. So I'm going to draw him in like extra bold. And in this case, every point on the line is a solution because these lines touch everywhere. These systems have infinitely many solutions. Every point that is on the line is a solution. Right? Every single point on the line is a solution. Every single point. Now that doesn't mean that every ordered pair imaginable solves the system. It means that every point on the line solves the system. So we still need a way to write down those solutions, and I'll show you how to do that. Before we get to that though, I just want to make sure we're comfy with these three possible cases. So the three possible cases are a unique solution, meaning one ordered pair solves the system, no solution, those lines never touch, there is no ordered pair that solves the system, or infinitely many solutions. Those are the three possibilities. Need to remember this. And whether you solve the system graphically by graphing the lines and hunting for that intersection point, or you solve the system algebraically using elimination or substitution, you will discover these. Graphically, you'll discover them from the picture. It'll be clear which case you're in. Algebraically, there are kind of hints along the way, and I'll work some examples to show you. We've already seen one example where there was a unique solution. I want to go through one more where the numbers aren't quite as simple to work with. And then we'll look at an example of each of the others. Okay. This is a little marked up. I'm going to do these all by elimination because that's how I want you guys to get comfy with these. Elimination is the better tool. So let's solve 2x minus 3y equals 0 and x plus y equals 1 by elimination. I could put both of these into y equals mx plus b, graph them, and then look for that intersection point. But I was told here to solve by elimination. So I need to choose what to multiply one of these equations by, and then add to the other to make one of the variables go away. That's the goal. If I multiply the second equation by 3 and add it to the first, then the y's will go away. See, there's a negative 3y here and a positive 1y here. So if I multiply this equation by 3, this is what I'm going to do. I'm going to multiply the second equation by 3 and add it to the first. Remember, what we do here is we add a multiple of one equation to the other. So first, let me multiply the second equation by 3. Let me show you what that looks like. First equation doesn't change. 2x minus 3y equals 0. And then if I multiply this equation by 3, every single piece gets multiplied by 3. So that's 3x plus 3y equals 3. So this is multiplying by 3. Multiply the second equation by 3. And now I'm going to add that to the first. So you can multiply through an equation by a non-zero number. All right, this is something we've seen before. You multiply both sides by 5, divide both sides by 7. That's always okay. It's okay here too. Now, if I add these, I have 2x minus 3y equals 0, and 3x plus 3y equals 3. And if I add those up, just like we did in the last one, 2x plus 3x is 5x. Negative 3y plus positive 3y is plus 0y. And 0 plus 3 is 3. We get 5x equals 3, right? 0y is 0. The y's go away. And this means x has to be 3 over 5. All right, this is our step 2 where we solve the result for that variable. And then my last step, I back substitute this into either equation. Sub x equals 3/5 into either original and solve for y. So I'll plug it back into the second guy. X plus y equals 1. If I plug in 3/5 for x, becomes 3 over 5 plus y equals 1. And then I can subtract 3/5 from both sides. And I get y equals 1 minus 3/5. 1 is the same as 5 over 5. So this is 5 over 5 minus 3 over 5. That's 2 over 5. So y is equal to 2/5. In other words, the solution is the ordered pair 3/5, comma 2/5. And that would be my final answer. Questions on these steps? Okay, I can show you in Desmos what this looks like. So yeah, this is Calc 2, you guys can see that. 2x minus 3y equals 0, looks like this. And x plus y equals 1, looks like this. So there's our two lines. And the intersection point here, they're giving it as decimals, 0.6, comma 0.4. But that's exactly 3/5, comma 2/5. Right, just written as decimals. So All is good here. Let's try to solve negative 2x plus y equals 3. And how about 4x minus 2y equals 0 by elimination. All right, I want to do the same sort of thing. I want to think about adding a multiple of one equation to another so that some variable goes away. Well, I have a negative 2x here and a positive 4x here. So if I multiply the first equation by 2 and add it to the second, the x's will go away. So I'm going to multiply the first equation by 2 and add to the second equation. When I multiply by 2, that first equation becomes negative 4x plus 2y equals 6. And the second equation stays the same. It's 4x minus 2y equals 0. And now if I add these, something strange happens. Negative 4x plus positive 4x is 0x. That's what we wanted to happen. But also here, 2y plus negative 2y, that's 0y. And 6 plus 0 is 6. So I get 0x plus 0y equals 6. In other words, we get 0 equals 6. That's some weird shit, right? Is 0 equal to 6? I don't mean to condescend. Yeah, 0 is definitely not equal to 6. I'm sorry, it looks like I'm getting an amber alert. So this means there's no solution. We call such a system inconsistent. All right, if a system has no solution, we call it inconsistent. 0 is not equal to 6, but this system is equivalent to saying 0 equals 6. So this system can't possibly have a solution. And in Desmos, if I graph those two equations, negative 2x plus y equals 3, and 4x minus 2y equals 0, you see they're parallel lines. Parallel lines with different y-intercepts, they're never going to touch. No matter how far you zoom out, no matter where you scoot around, those things are never, ever going to touch each other. So since the system, the solution to the system is the place where those two lines meet, the system has no solution. And that's it, you're done. Elimination picks this up right away. Substitution, you would have to go through the whole thing. And only at the end would you discover that there's no solution. It would still boil down to something like this. But you'd have to solve for one of the variables, plug into the other one, simplify, all that. and then get your 0 equals 6. Now, one more example like this. If I have x minus, say, 5y equals 2, and negative 2x plus 10y equals negative 4. And I want to solve by elimination. Something similar is going to happen. If I want to eliminate the x's here, I could multiply the first equation by 2 and add to the second. That will give me 2x minus 10y equals 4 for the first equation when I multiply it by 2. And the second equation stays the same, negative 2x plus 10y equals negative 4. And you can see what's going to happen here if I add these together. On the left-hand side, again, we're going to get 0x plus 0y. But on the right-hand side, we also get 0. So overall, what do we get? We get 0 equals 0. And this is true. A statement like this is called a tautology because it's true no matter what you plug in for x and y. So this tells me we have infinitely many solutions. In other words, these are the same line. And every point on those lines or on that line, they're really just one line, is a solution. The nice way to write all of these solutions is to solve one of the equations for x or for y. Let's solve the first equation for y. So what are they? Well, they're any point that's on the line. So if you take this guy, solve him for y, I'll subtract the x over, so I get negative 5y equals 2 minus x. Then divide both sides by negative 5. I get y equals negative 2/5 plus 1/5 x. I can say that these solutions are ordered pairs of the form x comma y. X comma negative 2/5 plus 1/5 x for any real number x. This is my set of all those solutions. So if you get through elimination something like 0 equals 6 or 1 equals 0 or something like that, then you have no solutions. If you get through elimination something like 0 equals 0 or 1 equals 1, then you have infinitely many solutions. If you have no solutions, then you're done. You just say no solutions. If you have infinitely many solutions, then you need to go back to one of the original equations, solve it for y, And then your solution set is all the ordered pairs x, comma, that thing you get when you solve for y. This piece right here is y. It is this thing that we got when we solved that first equation for y. These are just all the ordered pairs that are on the line. And there's really only one line here. All right. So this is everything I wanted to show you guys about systems of equations. Unfortunately, we haven't had time yet to talk about systems of inequalities, and we saw this coming. So what I'm going to do is this evening, I'm going to create an extra little video for you because we really do need to talk about that stuff. It's not challenging, but it's worth mentioning. I'm also going to open up a couple things for you to work on in MML. These are the last few things, but there are 2 more homeworks in here, systems of equations, systems of inequalities. So between now and the final, you have a few things to do. I'm going to post your take-home test. That's this tab over here in Overleaf. I'm going to finish buttoning up 1 or 2 things, then I'll post that. I'm going to unlock for you right now these last couple homeworks. They're not hard, I promise. And that is it. So between now and the final, I want you to please solve these remaining 2 homework sets. Again, I promise they're not hard. And work on your take-home test. Any questions for me?
Is the take-home test in Canvas or is it on my math lab?
I'm going to post it to Canvas. It's going to be a PDF. I'll just show you here. It's a PDF that you guys are going to print out. You're going to write your solutions directly on those printed pages, and then you'll scan them just like you've been scanning your written work and submit them on the day of the final. I will take it up to midnight on the day of the final.
Okay. When is the final?
The final for your class is on the 27th at 10:30.
So next Tuesday?
Next Tuesday, yep. So
Okay.
put this in your phone with a couple alarms, a couple notifications, remind yourselves. Make sure that you are ready and there on time because we are very rigid here at Santa Fe about when you can take the final. I'll have these homeworks due on the 27th as well. Oh, and there is a quiz associated with the systems of equations and inequalities stuff. So we'll have this open as well. I think, yeah, a quiz on 6.1 and 6.2. So between now and, yeah, okay, that's okay. So between now and the final, you have 2 homeworks and a quiz and that take-home test. So please don't forget to do any of these things. If you need help on the homework or quiz stuff, don't hesitate to come by office hours. I will be posting, like I said, 1 more video lecture on systems of inequalities. Okay, but you can go ahead and get started on the system of equations homework. That won't be difficult. I will post the take-home test for you guys right now, so you can get started on that whenever you choose. But I recommend solving the systems of equations homework first, then watch the video, then do the systems of inequalities, then do the quiz and the take-home test. Okay, that would be the order I recommend. And if you're having trouble with anything, you want to talk about anything, don't hesitate to send me a message on Canvas or to come by on office hour.
Okay,
the final is going to be on MML. So this class uses a department final. So every class has to take the exact same final exam. And since COVID hit, the way the course committee has been choosing to do that is on my math lab. It will still be using some proctoring software. I will make sure that to the best of my ability that we can still use HonorLock the normal way. It's a combination of multiple choice and free response problems. The free response problems is just like other MML, just like the homework, basically. The final exam is going to be just like the My Math Lab homework. Brooke, I'm not sure. They've been revising it. In the last committee meeting, I think the final exam had something like 30 questions. No, just 1 try, 1 attempt on the final. So it's just like a regular test. The only thing is it's going to be in My Math Lab. You guys will still write out your solutions. You'll still scan and submit those solutions to Canvas, and I will still look at those solutions as I grade so I can assign partial credit. So think of it as just like our regular Canvas tests. The only difference is it's going to be in MML.
Do we have to log in through Zoom?
I'll have to see what the department is saying. So I'll post an announcement with very clear instructions. Ever since COVID, they've been changing the rules for how we do the 1105 exams every semester. So we'll have to see what the course committee says. They'll send me an email soon saying these are the procedures for this semester, and then I'll immediately post an announcement. Best way to study is to make sure you've done all the homeworks. Make sure you're comfortable with all the homeworks, all the quizzes. And there is also a review for the final in MML that has been open for, I think, about a week now. So I would recommend taking a look at that. Yeah. So I popped this on 4/15. The review for the final is open. I'm leaving it open until the 28th in case you want to work on it after the final, because I do think it's worth some points in MML. And I don't want you guys to lose any points on a review. But yeah, first, make sure you've done all the homeworks and all the quizzes in MML. That's most important. Then do the review for the final. It's right there. There's also a review for the final. Although it is kind of old. If you go to the student resources page here, you saw what I did there. I just Googled Santa Fe MAC1105 final exam review. In this page, there is a link to an 1105 review for the final. You can check that out. There's also video solutions. You can check that out. There's a review for the multiple choice stuff. So there's lots of stuff here. Steve Grostefan is awesome. So I think you may enjoy that material. But again, these are kind of old. So I would recommend first make sure you do all the homework, then the review in MML. And then if you're looking for extra material, check out this page here. I'll copy paste it into the chat. All right, and you can also come talk to me in office hours. We can work extra problems. Just tell me, what is it you're nervous about? What is it you don't want to, you don't want to see on the final? And then we can work those problems together. I do think that the reviews, let me see here, how are they categorized? Yeah, I do think they carry some weight, yes. I don't want you to lose points on a review. If you don't complete a review, I don't think it should penalize you. So if you believe you have lost points due to not completing a review, let me know and I can go in and try to omit it for you. But of course, it is to your benefit to do the reviews. So I strongly recommend that you do it. Alrighty, gang, I got to get running. I've got an office hour that starts in a few minutes. You want to come talk more? Meet me there. Otherwise, I wish you all the luck in the world. And again, keep watching for that announcement regarding the final. Probably I will have you guys in Zoom. We'll try to do everything just like we do for our midterms, and I'll see you there. But if not, I wish you all the luck in the world on the final. Again, please don't hesitate to come ask for help. I'm available in office hours. I'm available over the weekend. Send me emails, whatever you need to do, just ask and I will help, okay? Take care, guys. It's been a wonderful semester. Good luck on the final.